Right, this is the final instalment. This feels like deja vu. So this is where you have got a second order differential equation, but it is non-linear because you've got x squareds instead of constants here and here, and to make this in the format that is solvable, we have to, or you will be given, a substitution to make to transform it to something that is solvable. And the usual thing to do, it's a very typical substitution to make, is the x equals e to the u, but you'll be told that anyway. Now, you've got to find part A. It says given that this, x equals e to the u, where u is a function of x, show that x dy by dx equals dy by du. And you can see there's mentions of y here, and there's no mentions of y within the substitution, so therefore we're going to have to involve it by differentiating with respect to y. So we're going to start off part A. We're going to get x equals e to the u, and we're going to differentiate it with respect to y. Okay, and what you end up with is dx by dy, and chain rule, differentiate that, you end up with that, but you must times it by the differential of the thing inside is du by dy. Okay, so we're going to reciprocalize both things here, so you end up with dy by dx is equal to 1 over e to the u dy by du. Times through by that, e to the u, and you end up with e to the u dy by dx is equal to dy by du, and you already know that x equals e to the u, so we can replace that with x. So finally you end up with, therefore, x dy by dx is equal to dy by du as required for part A. Okay, now the next bit, we've got to find something that's going to substitute d2y by dx squared. Well, we've got dy by dx, so all I've got to do is differentiate both sides with respect to x. Okay, so I'll do it here. We've got part B. Is a product, so you're going to differentiate the first to give you 1, leave the second, dy by dx, plus leave the first, x, differentiate the second with respect to x, you get d2y by dx squared, and that is equal to, now what we're trying to do here is differentiate dy by dx with respect to x. Okay, and we can't do that. Sorry, that's what, dy by du is inside there, and we're trying to differentiate that with respect to x. You can't, because the independent variable is u. Okay, and we're going to differentiate with respect to x. That's not possible. So what we have to do is use the chain rule here, and if you're trying to achieve the differential of dy by du by dx, we can look at it and we can differentiate dy by du, and we can differentiate it by what it needs to be differentiated by, is du, and times it by du by dx. So applying the chain rule in that way, we can now go ahead and differentiate that by doing this. Differentiate with respect to u. Well, this bit here is going to give you d2y by du squared. Well, we've got to times it by du by dx. Okay, and that is equal to dy by dx, and it's plus x d2y by dx squared. Now the next problem we hit is we're trying to find what that is. Well, if we go back to the beginning, you realise that x equals e to the u. So as x equals e to the u, we're going to differentiate this with respect to x, okay, and you end up with we're going to differentiate with respect to u is probably best, so you end up with dx by du. I'll write that down there, diff with respect to u, and then we're going to inverse it, reciprocalise it. Differentiate with respect to u gives you that, and that gives you e to the u. And I'm going to reciprocalise it, it's easier to do that, so you end up with du by dx is equal to 1 over e to the u. Resubstituting, because x equals e to the u, or as it says here, that is equal to 1 over x. So that can be replaced with 1 over x. Okay, so I end up with timesing, so I can cross that out and put 1 over x. Times through by x now leaves you with x dy by dx plus x d2y by dx squared is equal to d2y by du squared. Now that from the previous part A is here, x dy by dx is equal to dy by du. So that's dy by du. Throw it over, it becomes a minus. So finally we can say that x d2y by dx squared is equal to d2y by du squared, and it's going to be minus dy by du. Okay, and that is as required. That was part B. Now the question goes on to say we've got to use these two parts. It says hence, so we're going to use these two to find the general solution for this differential equation. Now the differential equation, if I quickly write it down, for part C is x d2y by dx squared. It is that's x squared. X squared, and I forgot to times through by x here, that should be x squared there, sorry, there. Okay, so that, and it is plus x dy by dx plus x dy by dx. We've got plus y is equal to 0. Well, that can be replaced with d2y by du squared minus dy by du, and the x dy by dx is replaced with dy by du. So it is plus dy by du, and I've got to add the y to it, and it equals 0. These two cancel out, and you're left to solve d2y by du squared plus y equals 0. Now this is a homogeneous solution because it equals 0, and it is linear. It's dead easy. It's got a constant here and a constant here, so we can now go ahead. The substitution we're going to make, because it's not dy by dx as we're used to, it's dy by du. So what we're going to make the substitution is y is equal to a e to the mu. Okay, so that's the thing we're going to try, and we're going to go straight to our auxiliary equation, augs eq. Okay, and we can go straight to m squared plus 1 is equal to 0. Solve this, m is equal to plus or minus I, and then straight to the solutions from there. You can see that y is going to equal to, and this is complex, so if you remember from the previous lesson, it is cos of 1u, so a cos 1u plus b sin 1u. Okay, now you can't just leave it in terms of u. This is the stage we're going to swing it back. So you end up with x equals eu. So x equals eu. So as x equals eu, we're going to take logs of both sides. Natural log of x is equal to u, and it's that substitution we're now going to make to get the final general solution. General solution, y is equal to a cos of ln x plus b sin of ln x, and that there is all there is to it. That's the general solution for the equation. Can't go any further because we don't know any boundary conditions. Okay, and that's it.